You've probably heard it 1,000 times, right? A squared plus b squared equals c squared. It's maybe the most famous equation in all of math. But have you ever stopped to wonder why it's true? It's not just some random rule somebody made up. It's the result of a really beautiful logical proof. So today, we're going to build that proof from the ground up. And I think you'll see it's way more elegant than you ever imagined.
I mean, just look at the trusses on this bridge. The whole reason this massive structure is so strong is because of the rigid, predictable shape of triangles. And what's the master rule that governs them all? You guessed it, the Pythagorean Theorem. So let's dive in and really unpack the elegant proof behind it. So here's our game plan. We're going to start by seeing how a single triangle can hide a whole family of similar ones inside it. From there, we'll build a neat little tool called the geometric mean. And only then will we get to the grand reveal, the Pythagorean Theorem itself. After that, we'll see how to use it in reverse, check out some handy shortcuts, and even learn how to classify any triangle you come across. All right, so our journey doesn't start with squares or equations. It starts with a simple right triangle and one single line. This first step, this one little observation, is the key that unlocks the entire puzzle. Here it is, the core idea that gets everything rolling. If you take any right triangle and draw a line from the 90-degree corner straight down to the longest side, that's called the altitude, you instantly create two new smaller right triangles. Now, here's the magic. All three of these triangles, the big original one and the two little ones you just made, are similar. That just means they're the exact same shape, like a set of Russian nesting dolls. And here's exactly what that looks like. We have our big right triangle ABC. We drop that altitude, the line CD, so it hits the hypotenuse AB at a perfect right angle. That one move slices the big triangle into two smaller ones, triangle ADC and triangle CDB. You can already see this hidden little family of triangles starting to take shape. This really shows you what we mean by similar. Just compare the little triangle on the left with the original big one on the right. You can see they both share angle A, right? And they both have a 90-degree angle. Well, if two angles in a triangle are the same, the third one has to be the same too. So they are the exact same shape, just different sizes. And guess what? The same thing is true for the other small triangle. This family relationship is the foundation for everything we're about to do. So what's the big deal about knowing these triangles are similar? Well, it means we can set up some really powerful relationships between the lengths of their sides. And these relationships, they're the tools we need to build our final proof. Because those triangles are all the same shape, the ratios of their sides are equal. And that gives us two really powerful formulas. The first one is interesting, but it's the second one that's the real key for us. It says that the ratio of a leg of the big triangle to the whole hypotenuse is the same as the ratio of the chunk of hypotenuse next to it to that same leg. Now, I know that sounds like a mouthful, but trust me, this special proportion is what we're going to use to construct the theorem. All right, the stage is set. We've got our similar triangles. We've got those crucial proportions that they give us. Now, it's time to put the pieces together and reveal one of the most famous theorems in the history of the world. And that theorem is, of course, the Pythagorean Theorem. You see, by taking those proportions we just established and just rearranging them a little bit, we get two small equations. When you add those two little equations together, something incredible happens. A bunch of terms cancel out, and you are left with this beautifully simple conclusion. A squared plus b squared equals c squared. It's not magic, it's not random, it flows directly from that simple fact we saw at the beginning, that a right triangle contains smaller copies of itself. Okay, so how do we actually use it? Let's take this triangle here. We know the lengths of the two shorter sides, the legs, A and B. Our mission is to figure out the length of the longest side, the hypotenuse, C. The process is super straightforward. We start with a formula, we plug in the numbers we know, so A is 3 and B is 4, square those, you get 9 and 16, add them up, and we see that C squared is 25. The last step is just to take the square root, which tells us our hypotenuse C has to be 5. It's just a clean, predictable process every time. So the theorem lets us find a side length if we already know it's a right triangle. But what if we're not sure about the angle? What if all we know are the side lengths? Well, it turns out we can just use the whole thing in reverse. This is called the converse of the Pythagorean theorem. It just flips the logic around. It says if you measure the three sides of any old triangle, and it just so happens that they fit the a squared plus b squared equals c squared equation, then bam! You know for a fact it must be a right triangle. It's a really powerful way to check for a 90-degree angle using nothing more than a tape measure. Now, this is pretty cool.
It turns out that certain whole numbers just work together perfectly in this theorem. They're kind of like pre-solved problems, and they can be incredibly useful shortcuts.
These are called Pythagorean triples. They're just sets of 3 positive whole numbers that fit the formula perfectly. The most famous one, of course, is 3, 4, 5, which we literally just used. But there are tons of others, like 5, 12, 13, or 8, 15, 17. And what's really, really useful is that any multiple of a triple is also a triple. So if 3, 4, 5 works, so does 6, 8, 10, or 9, 12, 15. You get the idea.
Okay, now this is where things get even more interesting. It turns out the theorem isn't just about right triangles. A little twist on the formula can actually tell us what kind of triangle we're looking at, whether it's acute or obtuse.
Here's how it works. You always have to let C be the longest side of the triangle. If C squared is bigger than A squared plus B squared, it means that longest side is kind of too long to make a right angle, so it pushes that angle open and makes it obtuse. But if C squared is smaller than A squared plus B squared, it means that side is too short and it pulls the other sides in, making all the angles acute. Let's try it out with a few examples. For a 4, 5, 7 triangle, we compare 41 to 49. C squared is bigger, so it has to be obtuse. For a 6, 7, 8 triangle, we're comparing 85 to 64. This time C squared is smaller, so it's acute. And how about 9, 12, and 15? Well, 225 equals 225. It's a perfect match, which confirms it's a right triangle. And hey, wait a minute. 9, 12, 15. Isn't that just our old friend, the 3, 4, 5 triple, but scaled up by 3? Yep. So think about that. We've gone from one simple observation about similar triangles all the way to a tool that can classify any triangle in existence. The logic is just flawless. And it kind of leaves us with this bigger question, doesn't it? This isn't just about triangles on a piece of paper. This rule seems to govern the very fabric of the space we live in. Why this rule? Why is it so fundamental, so perfect, so elegant? Now that is something we're thinking about.